Hello. Today we're going to be working through Chapter 7, Alkyl Halides, Nucleophilic Substitution, and Elimination Reactions. Up until this point, we've learned all of the basics that we need to start executing organic chemistry reactions, and today we'll be focusing on two of the most basic organic chemistry reactions that exist. So, to start with, let's look at alkyl halides a little bit. Alkyl halides are any carbon-halogen bond. We could have sp3 carbon-halogen bonds, sp2 carbon-halogen bonds, and sp carbon-halogen bonds. Alkyl halides are going to undergo both substitution and elimination reactions. So a substitution reaction is when we take an alkyl halide carbon bond and replace that bond with a carbon nucleophile bond. So we're substituting the nucleophile for the halogen. An elimination reaction involves a base, and we deprotonate a proton next to the carbon-halogen bond, and the halogen leaves as a leaving group to give us a double bond. So alkyl halides can undergo an elimination reaction when they're reacted with a base. In some cases, we have a reagent that can act as both a nucleophile or a base. So we're going to have a competition between the elimination and the substitution pathway. So we have a secondary alkyl halide in this case, and we have sodium hydroxide. We could obtain both the elimination and the substitution products. Generally, halogens are good leaving groups, and that's what they're used for in these substitution and elimination reactions. And this is because we're going to have a large electronegativity difference between the halogen and the carbon. This results in a partial positive charge on the carbon, which makes it susceptible to nucleophilic attack. In order for a molecule to undergo a substitution reaction or elimination reaction, it must contain a good leaving group. Good leaving groups are going to be the conjugate base of strong acids. So if we look on our pKa table, right, we have a number of acids that we consider strong acids. And so these are the best leaving groups, actually, the ones that have the strongest acid as their conjugate acid. So iodide, bromine, chlorine, these have very weak bonds with carbon and are very stable on their own. As we move to the weakest acids, we have the worst leaving groups. Alkyl halides are compounds where a carbon group or an alkyl group is bonded to a halide. And we're just going to go through quickly and overview how to name them. It's very similar to the naming protocol that we've used in the past. First, we're going to identify the name and name the parent chain. Then we work on the substituents, assign a location, and assemble them alphabetically. Here are a few example problems. In this case, we have a 7-carbon chain. If we start numbering from the left, there's a methyl group in the 2 position. If we were to start numbering from the right, there would be a bromine group in the 3 position. The 2 position is lowest with the methyl group, so we're going to start numbering from the left, and then we can assign locations to each of the substituents and then number them alphabetically. Since we have a stereocenter, we can confirm that the stereocenter at the 5 position is R, and so then we would have R5-bromo, 2,3,3 trimethylheptane. There are a few alkyl halides that we should refer to by their common name. One of the most useful organic solvents that we have is methylene chloride, and that would be the common name for dichloromethane. This solvent will dissolve pretty much anything that's organic. It's a very useful solvent, but it's also carcinogenic. We often use Greek letters to label the carbons And this is not just for alkyl halides, but also for other functional groups like ketones or alcohols. So the carbon directly attached to the functional group of interest would be the alpha carbon. The carbon directly next door would be a beta carbon, and further away would be gamma. We also have primary alkyl halides relative to secondary alkyl halides relative to tertiary alkyl halides. This is similar to carbocations. Depending on the number of R groups attached to the alpha carbon, we would determine if we have primary versus secondary versus tertiary. And the substitution of the alpha carbon is going to play an important role when we go to discuss which type of mechanism for substitution or elimination that these molecules undergo. There's a large variety of alkyl halides that are used as insecticides. So if we look at this molecule DDT, right, this carbon here would be the alpha carbon. It's alpha directly attached to this chlorine. One further down would be the beta carbon, and then these would be gamma carbons. Looking at lindane, right, the chlorine circled, our alpha carbon would be the one directly attached. The two carbons next door would both be beta carbons, and then these two carbons would be the gamma carbons. So the first reaction that we're going to go through is the SN2 reaction. This is a S substitution, N nucleophilic, and then the 2 is the bimolecular rate law reaction. The first thing we want to kind of look at here and understand is the mechanism. So we're going to be breaking a bond and making a new bond. We're going to be breaking a bond with the leaving group and making a new bond with the nucleophile at the same time. In the SN2 reaction, these bonds are both forming and breaking at exactly the same time. So we'll have nucleophilic attack where the nucleophile forms that new bond with the carbon, and then a bond breaking where the carbon halogen electrons go to the halogen. And that leaves us with the molecule with the carbon nucleophile bond formed, and then the leaving group as an anion. There is a second type of mechanism that could occur. In this case, instead of the nucleophilic attack occurring at the same time as the leaving group leaves, we have loss of the leaving group as the first step of the mechanism, and then attack of the nucleophile as the second step of the mechanism. So this is going to be a completely different mechanism, and since it's a different mechanism, it'll be a different reaction. For the SN2 reaction, we're focused on this concerted mechanism, where the two bonds are breaking and forming at the exact same time. And just kind of in summary, the S stands for substitution reaction. We're substituting the nucleophile for the leaving group. The N stands for nucleophilic, right, because we're doing a nucleophilic attack. And then the 2 stands for a bimolecular rate law, which we'll discuss a little bit more the kinetics of this reaction. So how does the observed stereochemistry in the following reactions support an SN2 mechanism? So one of the parts of this reaction that we want to look at, so we have the leaving group, carbon bromine, and we're going to form a new bond with the sulfur here. And notice that the bond being formed is on the opposite side of the bond being broken. And this is because we're going to have a backside attack of the nucleophile to the leaving group. Since the bonds are breaking and forming at the same time, every SN2 reaction that occurs on a chiral center is going to result in a flip of the stereochemistry. Since that bond needs to form and break at the same time, we're going to need to have the nucleophile approaching from the opposite side of the molecule as the leaving group. That's why one of the catchphrases for SN2 is the backside attack. The nucleophile is going to attack from the backside of the leaving group bond. So if we look at the carbon-bromine bond, we have the antibonding orbital here, and that backside is where the nucleophile will attack from. The electron density repels the nucleophile from attacking from the front side. The nucleophile must approach from the backside to allow the electrons to flow from the HOMO of the nucleophile into the LUMO of the electrophile. So we can draw the transition state of this reaction, and the transition state, we'll go through this in class exercises, but the transition state is going to include both a partial sulfur carbon bond and a partial carbon bromine bond. So it'll show a carbon almost being bonded to 5 atoms. And this transition state will explain why we get a flip or an inversion of the configuration. So earlier we discussed how the substitution of the halogens is going to play an important role in the reactivity. And the trend is that for an SN2 reaction, a methyl halogen or a primary halogen is going to be more reactive than a more substituted halogen, such as a secondary or tertiary halogen. This is going to be due to the steric hindrance, right? If a methyl group or a primary leaving group exists, then there's a lot of room for the nucleophile to attack. There's not much steric bulk in the way. However, with like a tertiary halogen, these methyl groups that are flanking the halogen are going to make it quite difficult for a nucleophile to attack. The further away the branching is, the less effect it's going to have on the relative rate of the reaction. But substituents at the alpha position are going to have a fairly large rate, whereas substituents at the beta position will have a much smaller effect on the rate of the reaction. But you can see even in this molecule here, we have a tertiary carbon in the beta position, and we still have a pretty significant decrease in the rate of the reaction. So here's an example of the transition state. We have cyanide acting as a nucleophile, forming a new carbon-carbon bond, and we have bromine as our leaving group. But in the transition state, we have 2 partial bonds, a partial bond being formed and a partial bond being broken. Let's take a look at how the substitution of the carbon will affect the rate of the reaction. If we look at the potential energy diagram of a SN2 reaction with a methyl substrate compared to a primary or secondary substrate, we can see that the starting energy of the starting material and the energy of the starting material and the products have the same relative energy. But the potential energy of the activation barrier is much lower with a methyl substrate compared to a primary or secondary substrate. There are several other factors that we need to take into account when we're looking at SN2 reactions. Each player of the SN2 reaction, whether it be the nucleophile, the solvent, the leaving group, or the substitution of the substrate, are going to affect the reaction differently. In general, we have anions that are often strong nucleophiles. So here's a list of all of the strong nucleophiles. And we have some weaker nucleophiles that aren't anions but still have a lone pair that can engage in nucleophilic attack. The reaction of a strong nucleophile is going to be very fast compared to a reaction with a weaker nucleophile. Halides are common leaving groups for laboratory use. So in organic chemistry, we'll often use halogens as leaving groups. But biology often uses different leaving groups, such as SAM, shown here, is a common leaving group that's used in biological systems. So both of these reagents, methyl iodide or a methyl attached to a SAM, are going to be methylating reagents, and a good nucleophile can attack the methyl group in either case. So when we have an alkyl halide that has a beta hydrogen and in the presence of a base, instead of a substitution reaction, we can also have an elimination reaction occur. This is a 1,2 elimination or a beta elimination and requires a hydrogen to be on the carbon next door to the halogen. A strong base will react in a concerted mechanism. So we have 3 arrows in this mechanism. The first arrow is a proton transfer from the beta proton to the base. Those electrons then go to form the double bond, which ejects the leaving group. So this is an E2 reaction, E standing for elimination. We're eliminating a leaving group. And 2 meaning that it has a bimolecular rate law. In this case, the rate is equal to the concentration of both the alkyl halide and the base. If we look at a molecule like this tertiary carbon attached to a leaving group, we could have hydroxide function as both a nucleophile or as a base. It's going to be much more likely to react as a base because of how substituted this carbon is. Remember, a tertiary carbon is not a good carbon for an SN2 reactions. It's too sterically hindered, and the nucleophile will not have good overlap to form the new bond. When it acts as a base, this primary carbon is less sterically hindered, so therefore we could have a elimination reaction occur much more readily. And these are going to form alkenes, so we'll just take a quick moment to go through Alkene nomenclature. It's going to be basically the same naming procedure as alkanes with a few minor changes. First, we identify the parent chain, and one of the biggest differences, the parent chain must include the carbon-carbon double bond. After we assign the locations and prefixes of each substituent, we give the carbon-carbon double bond the lowest number possible. The carbon-carbon double bond is also going to change the name of the prefix of the suffix to "ene." So instead of an alkane, we have an alkene. So to begin with, we can take a look at this example. We identify the parent chain. So in this case, we have 1, 2, 3, 4, 5 carbons. If we go up, we have 6, 7 carbons. If we go here, we have 6, 7, 8 carbons. But because the double bond is in this position, we're actually going to go with the shorter chain, but the one that contains the alkene in it. When we go to assign the location of the substituents and with the lowest number possible, we're going to want to put the alkene in the lowest position instead of a different substituent. So the correct way is to have the alkene in the 2 position instead of the methyl group in the 2 position. And then finally, the carbon-carbon double bond is placed just before the parent name or just before the ene suffix. So we can have 2 potential ways to name this. We can call it 2-heptene, or we can call it hep2-ene. Both of these are correct. A bit of review, we can have E or Z alkene stereoisomers depending on the atomic number of the substituents. So on each side of the double bond, we compare the 2 substituents. Fluorine has a higher atomic number than carbon. Nitrogen has a higher atomic number than hydrogen. So fluorine and nitrogen are the two highest priority, and they're on the same side of the double bond, so this would be the Z isomer. If we were to have the nitrogen on the opposite side of the fluorine, then we would have the E isomer. Because of the sterics of the two methyl groups overlapping with each other, cis isomers are going to be less stable than trans isomers. And there's a couple of different ways to visualize this, but more or less these two methyl groups are going to clash with each other in space and destabilize the cis alkene. We can compare mathematically the difference in this stability. We can quantify this by comparing the heats of combustion. And you'll see here that the cis isomer is going to have a larger heats of combustion because it is a less stable molecule. The more alkyl groups that we have attached to the double bond directly, the more stable the alkene will have. So on an increasing level of stability, we have a mono-substituted alkene with just one substituent attached. That's less stable than di-substituted, which will be less stable than a tri-substituted. A tetra-substituted alkene will be the most stable. In cyclic alkenes, we can only ever have cis alkenes because of the geometry. When we have a bicyclic alkene, if we have less than 8 carbons, then only the cis alkene is possible as well. If we take a look at these bicyclic structures, if we were to try to put a double bond attached to this bridgehead position, this would be a trans alkene, and it's not stable. Geometrically, this can't really exist. Here we have 9 carbon ring, and that is large enough to be able to facilitate the trans alkene. So the bridgehead carbon cannot have a trans pi bond unless there's at least 8 carbons in the ring. So with both SN2 and E2, we have to take a look at the geometry of the product. And in SN2, we're looking at the stereochemistry, so we're converting from R to S or vice versa because of the backside attack nature of the reaction. In an E2 reaction, we have to look at regioselectivity. So in this case, there are multiple beta hydrogens that can undergo elimination. Based on which beta hydrogen is deprotonated, we'll be able to obtain different products. So if we were to eliminate from this beta hydrogen here, we get what's called the Zaitsev product. And if we eliminate from either of these primary hydrogens, we get what is called the Hofmann product. So in general, the Zaitsev product is going to be the more stable thermodynamic product because we're forming a tri-substituted alkene in this case. The Hofmann product is going to be the minor product as it's the less substituted alkene. And that's when a ethoxide is used as a strong base or a sleek or skinny base is used. So this regioselectivity can be controlled based on the type of base we use. Using ethoxide, we obtained the tri-substituted. Now, if we use a bulky base, such as tert butoxide, we're going to be able to have less access to the secondary hydrogen because of the bulky base. There's going to be some steric interactions that prevent deprotonation at this position and make it easier to deprotonate at these primary positions relative to the secondary positions. So the bulkier the base you use, the larger amount of the Hofmann product you'll observe. A sterically hindered base is going to favor the Hofmann product. Here are a few examples of sterically hindered bases that you should add to your arsenal of reagents that we can use. let's take a look at 3-bromopentane. If we're to undergo an elimination reaction with this molecule, there's two types of stereoisomers that can be obtained. The major will be the trans isomer and the minor will be the cis isomer. And we can see that we just talked about the trans isomer being more stable, and so the relative energy of the trans isomer is more stable, and the activation energy needed to get to the trans isomer is also a smaller amount. An elimination reaction is going to be stereospecific. So let's take a look at this molecule here. We have just one beta hydrogen here. There's a terp butyl group on the other side. There's only one beta hydrogen to be removed, and there's two potential products, but only the E isomer is going to form. The only isomer that's going to form has the phenyl group on the opposite side of the terp butyl group. In order for us to rationalize this, we need to consider the transition state. And the transition state is going to require the 4 atoms of the elimination that are the 4 atoms that are affected in the elimination reaction to all lie in the same plane. They must be coplanar. The beta hydrogen in the leaving group must be coplanar. So we have to rotate the molecule in such a way that we have complete overlap of these orbitals. So if we rotate around this bond, there's two potential orientations where this can occur. There's the orientation where they're anti to each other, they're on opposite sides of the molecule, and then there's another orientation where they're on the same side. We can look at the Newman projections of these two. The anti-coplanar has the bromine and hydrogen staggered, and the syn coplanar has them eclipsed. The relative energy of these two Newman projections is going to be in favor of the anti-coplanar, right? The staggered conformation is much lower in energy because we don't have these eclipsed interactions between the terp butyl and the phenyl, the hydrogen and the bromine, and the methyl and the hydrogen. All we have is some of these gauge interactions, which cost us much less energy. So the starting energy of the anti-coplanar is going to be much lower than the eclipsed rotamer. As a result, the molecule is going to be in the anti-coplanar formation in a much higher amount. This is an equilibrium that the molecule is between, but it's highly favored in the anti-coplanar. If we flatten out in this elimination reaction, we can observe the final product's configuration by looking at the Newman projection of the anti-coplanar staggered. We can see that the phenyl and hydrogen are on the same side of the double bond that's going to form, and the methyl and terp butyl are on the same side of the double bond that's going to form. For the following substrate, the beta carbon has 2 beta hydrogens, so we're going to be able to obtain 2 different rotamers where the beta hydrogen is anti-periplanar to the leaving group. And so in this case, we'll obtain both stereoisomers. Since we have 2 hydrogens and free rotation about this bond, we could obtain either isomer. This reaction will be stereoselective, but not stereospecific. We're only going to have a stereospecific reaction when both the alpha and beta carbons have stereocenters. Because this beta carbon has 2 hydrogens attached, it is not going to lead to a stereospecific reaction. There's a big difference between stereospecific and stereoselective. In a stereoselective reaction, we have one molecule that can form 2 molecules, one of which will be the major product. And in a stereospecific reaction, we have two different molecules or conformations, each which can lead to a different product. In a ring, we're going to have to take this into account because we're going to have an equilibrium between the axial and the equatorial isomer of the chlorine leaving group. When the chlorine is in the axial position, we're going to have antiperiplanar with one of the hydrogens. However, when it's in the equatorial position, the antiperiplanar relationship is with a carbon. So the only way an elimination reaction can occur with a leaving group on a cyclohexane ring is when it's in the axial position, because that's the only way we'll have a hydrogen that's antiperiplanar to the leaving group. So keeping this in mind, let's take a look at these two molecules. Only one of them is going to be able to undergo elimination. Which isomer can undergo elimination? If we look here, the leaving group is trans to these two hydrogens. And here the leaving group is trans to two methyls. If you draw the chair conformation of these two molecules, you'll see that when the chlorine is in the axial position, these hydrogens are in the axial position, and when this chlorine is in the axial position, it's antiperiplanar to a methyl group. So only the trans isomer will be able to undergo elimination reactions. Sorry, the isomer where a hydrogen is trans to the chlorine. In this case, we have a potential to form a double bond at this position and this position, but the hydrogen attached to the tert-butyl group carbon here is cis to the chlorine. So we're not going to form that product at all. We'll only form elimination from the beta protons attached to here. In this isomer, we have a hydrogen that's trans to the leaving group, and so we'll form both products.